Kinetics, Equilibria, and Redox reactions. Definition of reaction rate: the change in concentration of a reactant slash product over time. The formula of the rate of reaction: the amount of reactant used slash product formed over time. Say the two conditions for a reaction take place. They need to collide in the right direction. They need to be facing each other in the right way. They collide with at least a certain minimum amount of kinetic energy. Kinetic meaning movement. Collide in the right direction, collide with at least a certain minimum amount of kinetic energy. Activation energy, the minimum amount of kinetic energy that particles need to react, at least need to have this energy to break bonds and start the reaction. Say I have to give particles extra energy, heating them. Maxwell-Boltzmann distribution curve, a graph of the number of molecules in a gas with different kinetic energies. A graph of the number of molecules in a gas with different kinetic energies. Entropy profile diagram: reactants, products, activation energy. Bonds within each particles are being stretched. It's an entropy profile diagram, entropy products reaction. That's the activation energy, this whole thing. If particles have enough energy, bonds break. And then that's that part. And then this is the energy barrier that particles have to overcome. And that's products progressive reaction. Maxwell-Boltzmann distribution curve, number of molecules, kinetic energy. Just looks like that. That's the peak. Peak represents most likely energy of any single molecule. Mean energy of all molecules is a bit to the right of the peak. Activation energy, only activation energy is there, and then this part is only particles that can react. Molecules have more than the activation energy. Curve starts at 0, 0, no molecules have 0 energy. Area under Maxwell-Boltzmann distribution curve is equal to total number of molecules. This part is equal to total number of molecules that can react with the total area. The area under Maxwell-Boltzmann distribution curve is the total number of molecules. Total number of molecules is the same, therefore area under both curves is the same too. And that's for something else, for the different temperatures as well. And that's it for this part. Yep. Nope. So, increase in temperature reaction, particles on average have more kinetic energy and therefore greater proportion of molecules with at least the activation energy and able to react. Pushes curve to the right. Molecules are flying faster, therefore collide more often at higher temperatures. And so here you go. No molecules kinetic energy. At 25 degrees Celsius, like that, that's obviously the activation energy. At 35 degrees Celsius, just pushed it to the right. So it's like that, pushed to the right. High temperature, more molecules have at least activation energy. If we increase the concentration of reactants in a solution where particles are closer together, collide more often / frequency, so more chances to react. If we increase in the pressure, obviously it needs to be a reaction involving gases, pushes all the gas particles close together, therefore more likely to collide, so more frequent collisions, increase reaction rate. Same thing as increasing concentration of reactant solution. Catalysts. A substance that increases the rate of reaction by providing alternative reaction pathway with lower activation energy. Catalyst is chemically unchanged at the end of reaction. So that's fine, but also include that if it asks you to define it. You include all of that, you should get 2 out of 2 marks. However many marks says catalyst, substance that increases the rate of reaction by providing an alternative reaction pathway with lower activation energy. Catalyst is chemically unchanged at the end of the reaction. Catalyst is chemically unchanged at the end of the reaction. Catalysts also don't get used up in reactions. We only need a small amount of catalyst to catalyze a huge amount of stuff remade at the end of reactions, and they only work on a single reaction. Nope. Wait. Apologies. Okay, so yes, this part and then this part for this, and that'll be the end of the video. So, entropy profile diagrams. Energy reaction pathway, that's the reactants. That's delta H to here, that's products. This is your activation energy with a catalyst. You can see it's a bit lower. This is activation energy without a catalyst, and this is energy profile diagram. Number of particles, energy, Maxwell-Boltzmann distribution curve, activation energy. More particles have at least the activation energy, and activation energy without a catalyst is there. Activation energy with a catalyst, this part, activation energy without catalyst, that part. Catalyst, it lowers the activation energy, therefore more particles with enough energy to react when they collide, allowing the reaction to go via a different route, therefore more particles react in a certain amount of time. Reversible reactions can reach dynamic equilibrium. A reversible reaction is a reaction that can go forward or backwards. So they can reach dynamic equilibrium. As reactants get used up, forward reaction slows down. As reactants get used up, forward reaction slows down. As more products form, reverse reaction speeds up. Dynamic equilibrium. When at equilibrium, the concentrations of reactants and products stay constant. When at equilibrium, the concentrations of reactants and products stay constant. Dynamic equilibrium can only happen in a closed system. A closed system meaning nothing can get in or out. Le Chatelier's principle. If a reaction at equilibrium is subjected to a change in concentration, pressure, or temperature, the position of equilibrium will move to counteract the change. Le Chatelier's principle. If a reaction at equilibrium is subjected to a change in concentration, pressure, or temperature, the position of equilibrium will move to counteract the change. Homogeneous equilibria, reactions where every species is in the same physical state. Homogeneous equilibrium, reactions where every species is in the same physical state, or liquid or gas. If you increase the concentration of reactant, equilibrium tries to remove the extra reactant, therefore making more product, equilibrium shifts to right. If you increase concentration of product, equilibrium tries to remove the excess product, therefore reverse reaction goes faster, equilibrium shifts to left. Catalysts have no effect on position of equilibrium, can't increase yield, however, they do mean equilibrium is reached faster. And then the redox reaction part. Oxidation, a loss of electrons, reduction, a gain of electrons. Redox, reduction, and oxidation happen simultaneously. Oxidizing agent accepts electrons and gets reduced. Reducing agent donates electrons and gets oxidized. So just think of the opposite. If the oxidizing agent is going to get reduced, so it's going to accept electrons. Reducing agent is going to get oxidized, donates electrons. And oxidation, loss of electrons, reduction, and gain of electrons. The oxidation state of an element tells you the total number of electrons it has donated or accepted. In a compound ion, the most electronegative element has a negative oxidation state. The other elements have a more positive oxidation state. That's really important. Compound ion, most electronegative element has a negative oxidation state. Other elements have a more positive oxidation state. Oxygen in peroxide has oxidation state of -1. Oxygen in OF2, oxidation state +2, O2F2, oxidation state of oxygen is +1, but oxygen in peroxide has oxidation state of -1. And you need to know these special cases because in the exam, when I ask you to calculate oxidation state, probably multiple choice questions, right, in paper 3, probably is going to be a special case rule. And if you don't know a special case rule, then you're going to be struggling quite a bit. So yeah, just learn these rules. H2O, oxidation state, oxygen -2. So oxygen in peroxide, oxidation -1. O2F2, oxidation state of oxygen is +1. OF2, oxidation state of oxygen is +2. H2O, oxidation state of oxygen is -2. But in H2O2, oxidation state of oxygen is -1. And that's a hydrogen peroxide. Oxygen peroxide is oxidation state -1. If it's anything peroxide, oxygen's oxidation state is going to be -1. Ionic half equations show oxidation or reduction, showing electrons gain/loss in the half equation. Yeah, and then that's really it for half equation, because then the next part is obviously constructing half equation and all that, and that's a skill in and of itself, and that just requires a lot of practice. But yeah, these are the key definitions, all of the key information. Combined hydrogen +1, right? So hydrogen always going to be +1, right? Except for in metal hydrides where it's going to be -1. So in sodium hydride, hydrogen has oxidation state of -1. So if it's hydride, sodium hydride, magnesium hydride, hydrogen is going to be -1, and that's another special case what we need to learn. Whereas HF, hydrogen is going to be +1. And let me just double check that's it. So that's done. That's done. Yeah, that's a different topic. And that's done.